To calculate and to compare the nuclear binding energy, I have to talk about mass defect first. Okay. All right. Let's say fluorine 19. Experimentally, we found that fluorine 19 weighed 18.9984 atomic mass unit. Okay. Now let's do some calculation together. That's experiment. But if we have let's say in theory, let's do some calculation. How much fluorine is supposed to weigh? Yeah, it's gonna be a different number. I'll show you. It's really interesting. All right, so calculated mass of fluorine. Well, the mass of fluorine comes from nucleus, right? 99.99% comes from nucleus, and the nucleus contains 9 protons and 10 neutrons. Okay, 9 proton. You know how much each proton weighs and how much each neutron weighs. So 9 times that number, so you get that 9.06552 AMU. 10 neutron weight that. The total of the mass of fluorine is supposed to be 19.15222 AMU. But experimental mass is only 18.9984. What's going on here? Well, so there's a mass difference there. Can you see that? So the mass difference is right here. So 19.1551522 minus 18.9984 equal to that number. What's going on here? Proton and neutron come together from a nucleus and mass is gone. So the loss in mass that occur when proton and neutrons combine is called mass defect. Okay, that's a mass defect. Well, so basically this is what happens. So we have a 9 proton and 10 neutron combined to make a nucleus of fluorine. The mass gone. That amount of mass is gone. I'll take a look here. So some mass somehow got out of this nucleus and it's gone. And it becomes an energy. Whoa. What's going on? This doesn't make any sense. Mass and energy? What? Well, there was one person who said that, well, you can relate mass and energy, and I'm sure you know this guy. His name is Albert Einstein. Well, that's his famous equation, E equal to mc squared. Mass and energy can be related, right? Can be related. So plug the mass defect into this equation, and well, of course, this is physics now. We have to convert AMU to kilograms, right? And kilograms will time the speed of light square, right? And you're gonna get that number. That's a mass release. Okay, so release 1.3842 times 10 to the 10th kilojoule per mole. Now, is this energy a lot? Well, let's compare to the energy involved in a regular chemical reaction. Okay, let's take a look. In a regular reaction, we have talked about this. So a regular chemical reaction produce or absorb heat about that amount kilojoule. Compare this to 10 to the 10th. Oh my God, that's a lot of energy. See that? That's a lot of energy released when just small nucleus is formed. All right, so that's the amount of nuclear binding energy. It's a lot of energy. That's the reason why you need to have a number of neutrons, and that's the reason why all protons, they come together. This energy overcome the proton and proton repulsion. It's a lot of energy. Okay, all right, moving on. So a little bit more about nuclear binding energy.